PTH and this calcitonin.
Do people lose calcitonin as they age?
Pardon me?
Do people lose calcitonin as they age?
Well, that all depends on your thyroid function. If your thyroid is functioning normally, no. And same with your parathyroids. These are like P-shaped glands on the back side of your thyroid. Your thyroid is located about up in here. Okay, it kind of is around your larynx. Under normal conditions, well, everything sort of gradually drops off as we age, but under normal conditions, no. You know, you will deposit new bone matrix depending upon your activity, and your bones, like your muscles, will respond to stress. And what I mean by stress is weight bearing by either increasing in density or decreasing in density. Here's an example. From the day we come out of the cereal box, we're fighting gravity. So we're putting stress on our bones and on our muscles. And so they get bigger. Okay? Now, let's say, take you or I, and we go up to the International Space Station, and we spend 3 or 4 months. All right? Well, one of the reasons why spending extended amounts of time up there is not good is because the amount of stress, and again, weight bearing, that's put on your bones and on your muscles is gone way down because you're in a zero gravity environment. I think the record, if memory serves me correctly, the record for the longest amount of time spent in space was 180 days, somewhere around there. It was a Russian cosmonaut, but when he came back down to Earth, he had lost so much mass in his bone and his muscle, he had a very difficult time walking. And that's why, that's one of the things NASA works on a lot, you know, to conquer space travel or interplanetary space travel, because you're up there a long time in a microgravity environment. So you're not working stuff out, and so mass starts to decrease. All right, these two are important, so I would put a little asterisk by them and realize that these two hormones, and they work by negative feedback. In other words, if calcium levels get too low, beyond the homeostatic parameter, then we release PTH. If the calcium levels get too high, above homeostatic parameter, we release calcitonin. Calcitonin stimulates the osteoblast to deposit the excess calcium, among other things. It does things in the kidneys as well to rid the body of excess calcium. Okay. As far as any other, real detailed information about the microscopic structure of the bone, the hard bone. This is all hard bone. Okay, this osteon is associated with compact bone or hard bone, and then the cancellous bone, it's arranged in this needle-like, thread-like arrangement called trabeculae. But again, trabeculae. The cancellous bone is found in the epiphysis of long bones, and it makes up most of flat bones. All right, like the skull and like the hips.
But that's figure 7.9?
Yeah.
Okay.
So when you look at those, all right. So just to kind of wrap it up and to note things that are important to focus on, the cell types: osteocytes, osteoblast, osteoclast. The basic difference between hard bone or compact bone, you'll hear it referred to as compact, hard bone. Hard bone is arranged in these osteon sort of arrangement, is series of concentric rings. And then the cancellous or spongy bone is arranged, CE, in this trabeculae arrangement, if you will, okay? All right. Make a note on the two hormones that are used to regulate serum calcium, because when you talk about bone, you got to talk about calcium, okay? All right. Let's move on there. Two types, real quick, because I'm going to just try to touch a little bit on everything, or as much as we can. Bones, we start off our lives, by and large, you know, after the sperm meets the egg and goes through multiple series of cell divisions, and we start to develop a skeleton, if you will. Well, our first skeleton is made up of the cartilage, hyaline cartilage. Now that's advantageous because, you know, we're in a shape, living in a rather cramped underwater environment, and we have to be very, very flexible. And this cartilage is very flexible. All right. And this hyaline cartilage, you know, sometime, I don't know, I won't say exactly, but, you know, around the 5th, 6th month of gestation, that cartilage starts to harden or go through a process called ossification, where it starts to become bone. And you can look, if you're looking at diagram figure 7.5 on 185, you'll see
That's 7.5 is, I'm sorry, excuse me.
Yeah, 7.5.
I was thinking something else.
And what this is the two types of ossification. What 7.5 shows you is a type of ossification called endochondral. And literally what that word means, endo means
Inside.
inside, and chondro, or chondral in this case, means cartilage. All right, so these bones start to form from a hyaline cartilage model. Now, I'm not going to get real picky and differentiate between the primary ossification center and the secondary ossification center. But what is important about this, well, first let's mention the second type. There's endochondral, inside the cartilage, and then the second type is intramembranous. All right, intra means
Inside.
within or inside, and
Membrane.
inside a membrane, some type of membrane. Okay. Now, different bones, most of the bones will form by this endochondral, are long bones. Okay. The bones, say, of the skull and say the hip girdle will form by this intramembranous within a membrane. Now, why is that important? Well, we know that when we're born, it's like if you're having a vaginal birth, it's like you're squeezing, the woman is squeezing a golf ball through a garden hose, right? And so, in order that we don't experience a great deal of brain damage as we're coming through the birth canal, our skull changes shape. It's squeezed, it's pressed, but it's not crushed, because the fetal skull, as we're coming out, has not completed this intramembranous ossification process. And if memory serves me, that doesn't happen until we're about 14 or 15 years old. You know, kids are the so-called soft spots in their heads. Well, that's the remnants of these membranes from within which the skull formed, okay? Those remnant membranes in the fetal skull are called fontanelles. I think it's just one S. Okay, and you have, if you look at on the opposite page, figure 7.4, you'll see a fetus as it's developing, and you'll see the intramembranous skull bones forming in the skull, and then you look at the long bones, and it'll point to, you know, like the long bones of the arm that are forming by endochondral, okay? These fontanelles are important because all that pressure on there does not get transmitted to the brain tissue, because the skull can kind of change shape and make its way through the birth canal. You know, they say sometimes kids are born with a cone head, but you know, it relaxes after a while and takes on its normal shape. All right, and again, I'd have to look it up to be exact, but I don't believe that complete ossification of the, particularly the skull, by intramembranous ossification occurs until we're about 14 or 15. Okay, all right, remember those. Endochondral, from within the cartilage model, and intramembranous, from within these fibrous membranes. And again, if I were to, you know, most of the bones of our body form by endochondral. Okay, if we're looking at like the skull and the hip girdle, they're going to form by this intramembranous method. Okay, these fibrous membranes that form the fetal skeleton go through a similar process where blood vessels penetrate and matrix gets laid down, but I'm not going to get real picky on that. We don't really have to go into great detail about the particular differences between these two types, but just know that there are two types. And it's important because they'll say, well, you know, why does a fetus have these so-called soft spots on their head? And it's because the bones have not completely ossified, okay, and formed one skull. When you look at the human skull and you peel away the hair and all the tissue underneath, you see these remnant lines in the skull, right? Have you ever seen those? All right, well, let's take a look at those just to show you what I'm talking about. Yeah, look on page 195, figure 712. Okay, or even there, it doesn't matter.
All right, 712.
You see these remnant lines between these different bones of the skull. These remnant lines are joints. Okay, the skull is not just one big bone, but a compilation of several different bones.
They're not called plates, though, right?
They're not called plates, they're called sutures.
Okay.
Okay, for instance, when the frontal bone and the parietal bone finally do ossify, what's left over after that is this remnant line, and it's called a suture. And, you know, most people don't think about that as being a joint, but it is a joint. It's an immovable joint, but it is a joint nonetheless, okay? All right, let's go back and let me just kind of keep these things in order. We know the cell types. We know some of the functions of our skeletal system. Obviously, a primary function is to provide for movement, right? It gives muscles something to attach to provide for movement. Second primary function we've already addressed, that most people, I won't say most people, but that folks often overlook, is
Red blood cell formation?
red blood cell formation. You know, you don't typically think of your bones as being important in doing that, but yes, they do. They also serve as a depot or storage deposit for these minerals, these inorganic salts called calcium and phosphorus. Okay, and if you look, and you can make a note of this, on figure 7.8, page 190, we're looking at this negative feedback mechanism for controlling serum calcium. You see that there?
Yes.
All right. We start off with a normal serum calcium in the middle. When the calcium's too high, all right, that's the stimulus. Okay, receptors in the thyroid gland sense the increase in serum calcium. So what do they do to respond? They release calcitonin. And calcitonin
affects the
osteoblasts, which function to...
Blood calcium level returns to normal.
Right, they deposit this excess calcium into the bone matrix and return, when the serum calcium reaches the homeostatic parameter, then the stimulus is shut off. Conversely, on the opposite side of that, the stimulus is that your blood calcium is too low. What responds, the receptors are
parathyroid,
PTH or parathyroid, and they secrete a hormone called parathyroid hormone or PTH. And what the function and what the response of that is, the effectors, what that works on are the osteoclasts, which break down bone matrix to release calcium back in the blood. Once the calcium level reaches its normal homeostatic parameter, then the stimulus is shut off and we're back to normal. Okay? All right, that's important, so let's remember that. All right, now, just moving along. Our skeleton is divided into two primary skeletons. We have, okay, we've been over the cells enough. We have the axial skeleton, and we have the appendicular. And not too difficult to differentiate if you think about the words. Axial is going to run down the axis of the body. All right, so if you look at the axial, it includes the skull, the sternum, the ribs, the vertebral column, and the sacrum, because that runs down the middle of your body, the axis of your body, okay? So we have the skull, vertebral column, the sternum, ribs, and the sacrum, okay? The appendicular, your appendages in your body, are your arms and your legs, right? These are our appendages. So the appendicular is the scapula, or the shoulder blades, Michael. Arms, hip girdle, G-I-R, I'm not spelling too well today, and legs, and of course feet. When we talk about the arms, we're talking about the hands. Okay, these are our appendages. Now, I'm not going to ask you what are the name of the 6 wrist bones. If you want to know that, look them up. What's the point in trying to remember what they are? I would be able to differentiate between what is part of the axial skeleton and what is part of the appendicular skeleton. Now, as I kind of pointed out a little bit earlier, remember the skull is a compilation of several different bones. The bones are named according to the lobe of the brain which they overlie. All right? So you have a frontal bone, one. You have two parietal bones. You have two temporal bones. And this is looking at just on the outside. And you have one occipital bone. So when you go through and you just look at the bones of the skull, just be able to say, well, yes, I only have one frontal bone, two parietal, two temporal, one occipital, one sphenoid, and that's looking on the inside. Now,
so that would be on table 7.1, axial skeleton?
Yeah. Actually, if you want to look at the bones of the skull, look at figure 7.12.
7.12, okay.
Yeah. You'll see a frontal bone, a parietal bone, a temporal bone, and an occipital bone. And then you'll see the bones that make up the face, okay, which are the mandible, right, 7.12.
Got it.
Okay. The mandible, the jaw, the maxilla. All right. And you'll see the zygoma that make up the cheeks. And that's just a matter of kind of looking at them, maybe writing them down one time. And the point is to realize is that it's just not one solid bone with one name. And a way to remember that, if you look at the orbits of our eyes, where are the globes of our eyes, or our eyeballs fit, people say, well, that's just a hole in there. Well, no, it's actually the union of 8 different bones. For instance, we have a lacrimal bone. And you look at the orbit here. You'll see that you have a lacrimal bone, part of the ethmoid bone is there, part of the frontal bone makes up the roof, part of the maxilla makes up the floor. You have the sphenoid, makes up part of the lateral aspect of that. You have the temporal bone. Okay, so this, just know that the orbit where the globes of our eyes sit is not just a hole in these bones. This is where bones have come together, where they have ossified and formed these immovable sutures, okay? Okay, what's important? Look at them, but more important of that is in the vertebral column, we have to know that we have, under normal conditions, we have 7 cervical vertebrae. We have 12 thoracic, and we have 5 lumbar. Okay, and there are S1 through F, 5 sacral, but these are all fused into one. And then we have between 3 and 5 coccygeal, the so-called tailbone. All right. So we have 7, 12, 5, 5, and between 3 and 5, depending upon the person. That makes up your vertebral column. Important to remember in the vertebral column, in every one of these vertebrae, except for the sacral and the coccygeal, the cervical, thoracic, and lumbar, there is a hole. Okay, and in that hole is where the spinal cord lies. All right, now in the average adult, the spinal cord, before I say that, these are given numbers, okay? We call these are C1 through C7. Starting at the top. Now, of note, C1 and C2 sort of have special names. C1 is called the axis, and C2 is called the atlas. Okay, and remember that picture back in the old days, Atlas holding the world? Well, your atlas is holding this big ball on between your shoulders. You have 7 cervical, C1 through C7, 12 thoracic, labeled T1 through T12, and it starts at the top and goes down, T1 through T, and lumbar you have L1 through L5. And I try to bring this to light to say that, have you ever had surgery on your neck?
I've had surgery on my lower back. I've had lumbar.
You've had lumbar surgery.
L2, L3, and L4.
Okay. I've had 3 different fusions in my neck. So literally C1 through C7 have been fused into one bone, held together by cadaver bone initially, now my own bone, but also these titanium plates. And you've had lumbar surgery, so you know what we're talking about. They fused it.
Actually, they did not fuse it. They said it was fused through arthritis. So
well, that happens.
Right.
Yeah. They took
they took the back off.
The discs out.
Yeah.
In between
decompression, they call it.
Huh?
Decompression.
Yeah. Well, what happens is in between these vertebrae is you have this sort of gelatinous disc, cartilaginous disc, but it's kind of gelatinous as well, that has 2 components to it. And what that does, that disc in there serves as a shock absorber. Because think about it, even from the day we come out of the box, we're subject to the force of gravity, and there is a lot of pressure put on our spinal column. And this helps to absorb the pressure. If you've had the so-called herniated disc or a ruptured disc, what ruptures is the nucleus of this gelatinous, well, the material on the inside is more gelatinous, it's more cartilaginous on the outside. The inside is called the nucleus and pulposus. Now, why do I bring that up? Because in your medical coding, you may see a reference made to what they call an HNP. And you'll have to assign a specific code to that. An HNP is a herniated nucleus pulposus. And what happens is that this sort of gelatinous material, because of stress and all this wear and tear on it, it sort of oozes and makes its way through the cartilage matrix. And what it does, you have spinal nerves that run along here, and it puts pressure on those nerves, and nerves don't like pressure. And and in general, the way, and we'll talk about this more when we get to the nervous system, but the way that a spinal nerve is organized, on the outsides of the tracts are sensory nerves, and on the insides of the tracts are motor nerves. Now that's just a generalization, but we can use that as a way to explain it. So when this thing herniates and pushes on there, first thing you're going to feel is pain. If it progresses, and it starts, well, that's still sensory. Okay. But if it continues and it starts to press on the motor,
you lose function.
You lose function. Yeah. And that's what happened to me with my neck. I had pain right in the middle of my shoulder blade there, and I said, I've been out, I was much more active back then, cutting wood, stacking wood, cutting grass, doing whatever, so I just blew it off. Well, this was when my child was an infant, and one day I went down to pick her up, and I'm going, damn, there's something wrong, it wasn't that easy. And I got to a point where I couldn't pick her up. because I was pressing so hard in on the spinal nerve that I was losing function. All right, remember and I bring this up, you know, a lot for for those who go into medical coding, because you're going to see they're not going to call it a herniated disc. I don't believe. They will call it an HNP, herniated nucleus pulposus. If you want to know the other name for the outside, is called the nucleus fibrosus. All right, but what herniates is the pulposus. Okay, so in between the cervical, thoracic, and lumbar, and between the lumbar and the sacral, there's a disc. You have these intervertebral discs, serve as shock absorbers. I will bring this up because it's important, because you may be asked this. A unique feature of these cervical vertebrae is that they have what's called, that are not found in the thoracic and the lumbar, and of course not down here, but they're called transverse foramen. All right, now a foramen is a term that generally means it's just a hole. Okay, now I had told you that here's the, you know, like the body of a vertebrae, and well, let's look at a composite of a vertebra just so you know what I'm talking about. And you can see where that hole is. Look on page 201, figure 7-8.
Okay.
Okay? Mm-hmm. We're looking at cervical vertebrae, thoracic vertebrae, and lumbar vertebrae. Now, obviously, the bodies of the lumbar vertebrae are the largest. Why? Well, because they're at the bottom and they're subjected to the most stress. The important thing that I was telling you here is that you have these holes in the transverse processes of the cervical vertebrae called transverse foramen, which you do not see in the transverse processes of the thoracic or the lumbar. And you say, well, why are they there? Well, because you have 12 cranial nerves that come from the brain, and they come out to service, you know, the upper extremities, and they pass through these foramens. In general, when you see the term foramen, it's just a hole, and it's a conduit, a passageway for nerves, blood vessels, whatever. Okay? Any foramen. Okay? But I bring that up because the thoracic vertebrae and the lumbar vertebrae do not have transverse foramen. So if you're looking at a diagram of a vertebrae and you're not sure where it's from because you're not quite sure if the body's big enough to be a thoracic or lumbar, look at the transverse processes. If there's a hole in them, you're looking at a cervical. Okay? All right. I was jumping ahead just a little bit, but a lot of this, you're going to have to look at the bones, and I won't go spend time looking at those just to identify them. For instance, look on page 196, figure 714. There's a big hole at the bottom of the skull there, called the foramen magnum. Foramen meaning hole, magnum meaning large. Well, what do you think comes out of there?
Spinal fluid?
Spinal cord, yeah, sure.
Okay.
That's where your brainstem